Okay, so last we stopped is on the room acoustic. So this is still topic two lah, regarding the acoustic system or the sound and acoustic system noise control. So when it comes to room acoustic, there's a principle behind it lah, which is the concern regarding the control of noise within an enclosed space. So hopefully you guys still remember what this subject is all about. This subject is about building science and services, meaning we understand what is the services implemented inside a building. So previously we learned what is noise about, how we perceive noise is all movement or transfer of energy in the air, and how we pick up all this signal is all just how we perceive all this sound is all just actually in our head. So if you don't have the function, the hearing function, then we actually will not be able to hear any sound. So actually this is all in our head, and we are actually unable to turn this function off because this is how we are made lah. So when it comes to our lifestyle, then we will want to have a certain room acoustic. So maybe it can be due to our work nature, or maybe because we are working in a place. So when it comes to doing work in a place, then different career will require a different level of room acoustic. So if you're just working, you just want a acceptable noise level lah in a room. But when it comes to, let's say, recording music, then this is where this room acoustic is very important. So as you can see in this picture, this is not a very good one lah. So if you can see here previously, this is the setup of a room where it will be a very very quiet room because we have a lot of insulation layer that's there to absorb the sound. So this sort of room will be very good when we are recording music. So there's a difference between a very good room, a room which has a very good noise barrier, or a room which has a very very good acoustic. So a room which has a very good noise barrier, meaning that outside noise doesn't really come inside. You won't hear any external noise. But when it comes to room acoustic, then it's more of the room being very very quiet. There's no any background sound. That's the first one. And then secondly, the sound in the room, there's no reflection. So this way, when there's no reflection, whenever all the sound that you generated will be clear lah, and then that's what you want to record. So this is what it means by having a good sound, a good room acoustic. So the keyword here is the production and reception of sound. Usually this is for music lah, the way we set it up. Okay, you have 5 general requirements. So the first is, if you want to have a good room acoustic, generally you do not want to have any background sound being heard lah when you're in this room. And then secondly, you want to have a good enough sound level, even distribution of sound to all the listener in the room, and then you don't have any reverberation of sound, meaning there's no reflection, or the rate of decay is very good. And then lastly, you don't have echo. So reverberation and echo is very, very similar. So echo is a reflection of sound which comes a bit more slower, and reverberation is a reflection of sound which comes very, very fast. So it's more of a reinforcement of sound. But usually when it comes to recording of music, we actually do not want to have all this extra reinforcement lah. So you have software to actually improve or adjust the music, the quality of the music. So echo you guys should be familiar with. It comes like it reflects the sound about 1 to 2 seconds later. Reverberation is the type of sound that you experience if you're in a very big orchestra, so or in a very very big building. So the sound counts back very very quickly, like maybe 0.1 second, or maybe in a bathroom. So a reverberation effect is where you experience it in the bathroom, where the sound will try to amp, where the sound generator will amplify itself. So just a bit of info here. Okay, so next on we have reflection. So based on how sound is generated or how sound work, they are actually the same way as light. So because of their property, they can be reflected, but this is provided that they are the reflecting object is a lot bigger than the wavelength of the sound lah. So if the reflected object is smaller than the sound, then there won't be any reflection. So the sound will just bypass the object lah. Usually this reflecting object will be a wall, or in most cases in a building, the four corners of our wall. So you will notice that in a room, if our room do not have anything, let's say lah, for example lah, since when one day you find yourself in a situation where you enter a room that do not have anything, there's only four sides of wall, you'll notice that this room will have echoes or reverberation. So why is that? Because whenever you talk or you produce a sound, this sound wave, they will bounce itself off the wall and back to you. But in the same case, if you're inside the same size room, but if you put a lot of object in the room, meaning you store a lot of stuff, then you actually find that this particular room, you do not experience the same level of reflection, the sound reflection. So this is because there's a lot of uneven surface that actually absorb the sound, but they won't be very good in absorbing the sound lah, because they are not there to their function is not there to absorb this sound. Okay, so there's two things regarding reflection. So when you're reflecting surface in a room are used to help the even distribution of sound and increase the overall sound level by reinforcement of the sound wave. So this is talking more towards the reverberation. And then secondly, you have reflection effect. So reflection near the source of sound can be useful. Reflection at the sound at distance from the source may be troublesome. So when it comes to sound being reflected nearby, it will be a reinforcement effect. But if it's at a distance, then it will be an echo. So it's a nuisance. So you don't want to have something that repeats itself a few seconds later. But if it's a sound that reinforce the quality of the sound, then it's actually very useful lah. So as mentioned, if the sound comes a bit later, then it's actually considered or called as an echo. So echo is a delayed reflection. So it can be perceived. It's not a very good effect lah, or from the generation of sound. So what we want to do is we want to minimize the echo by using absorber or any surface that can absorb all this additional sound. So if the echo is very very strong, then it will actually affect the sound generation in this building. So we do not want that lah when we build a building. If that is a case where there's echo being generated in a building, then you want to install additional material on the surface so that we can absorb all this unwanted noise. So if you can see at the bottom here, so you notice that all the all the movement of all this sound, they are actually moving all around in a room. So the way they move is very similar to how light move. So the principle behind sound and light are very closely related. So when they move at one angle, they will be reflected the same. So a bad room acoustic will have a very delayed sound effect, which we do not want. Therefore, you need to learn how to reduce all these reflection of the sound inside a building. So this section of the topic 2 is more concerned regarding the room acoustic. So just an example lah. We have a Royal Albert Hall in London, and this dome ceiling actually causes a very unsatisfactory acoustic and requires remedy. So instead of giving a very good sound quality back, reinforcement of sound quality back, most probably this building produce more echo. So to reduce all this echo, we can install all this insulation material, which is a material wool or fiberglass, for example. So this material is a very porous material. So what it means by porous, meaning there's a lot of air. It's a very fluffy material, meaning there's a lot of tiny air pocket inside this material, both the mineral wool and also the fiberglass. So this is how absorbent material is like. So when you generate a sound and when the sound hit this, then instead of what you learn on the previous session, where the insulation of sound is governed by four these four principles: heaviness, isolation, completeness, and flexibility. The principle behind sound room acoustic is more towards absorbent, not insulation. End product, they generate the same effect, but when it comes to a good room acoustic, you want to have noise absorbent. So they both have about the same effect. They can both cause the same effect, but the function is different. Room insulation, noise insulation, and noise absorbent. So noise absorbent will be more concerned with the acoustic of the room. Okay, so we actually have three type of sound absorbent. So we can have a porous absorbent, which is the mineral wool or the fiberglass. So a bit more in depth will be they will have a good effectiveness at a frequency of 1 kHz. And then next we have a panel absorber. So usually this is from materials such as plywood or suspended ceiling, and you have a space behind that. So this is absorbing the energy and converting them into vibration. And they are good for frequency from 40 Hz to 400 Hz. And then there's a cavity absorber. So you notice that we have these three different type of absorber. So based on what is the function or the usage of this room, then we can decide whether or not to use the porous absorber or the panel or the cavity. So you need to find out what is the frequency of the sound being generated And based on that frequency, you should propose the correct type of absorber. So some absorber are better at reducing the sound at this frequency. Another is at this frequency. And finally, we have this cavity absorber, which can absorb resonant frequency, which can absorb the maximum lah, but it will be the most complex. So a panel absorber will be something like this. You have a plywood, and then we have an air gap. So when the sound hit this material, they will be converted from the sound energy to mechanical energy. So this way, instead of the sound being hitting a very rigid surface and being reflected back, a sound absorber works by converting this sound energy into another form of energy so that this sound energy does not reflect back to the source. So this is the function of a sound absorber. So this is how a panel absorber works. So cavity absorber will absorb all the sound into this cavity. And then the idea is when the sound enter the cavity, they should lose their energy when they are inside this cavity, meaning they bounce around inside and then they should lose all their energy. So they all have different way, and to implement it, it will cost a different budget lah. Okay, so next off, we want to talk a bit about the reverberation. So if the main source of sound suddenly stop, it is unlikely that the sound in the room will also stop suddenly because sound is actually a movement of energy. So there will always be a continuous presence when we're inside a room because sound is always being reflected. So that's why we have reverberation as seen here. So reverberation is a continuous enhancement of a sound caused by rapid multiple reflection between the surface of a room. So it's only in a room or in a place or in a very unique situation where reverberation happens. So if you're out in an open field, then there's no reverberation because reverberation happens when something is being reflected back, when your sound is being reflected back to the listener. So if you're in an open field, reverberation cannot happen because the sound is being dissipated all around you. So basically, when it comes to a comparison between reverberation and echo, they are basically actually the same thing, except one is shorter. They have a shorter wavelength, meaning they come to you very fast, which is reverberation at 0.1 second. And then the other one takes a longer distance to travel to return back to you, which is close to 1 second or more than that. So reverberation can add or enhance the sound, but echo is not. It will be perceived as repetition because when it comes to echo, you will be able to intake or listen to the original sound, but then the reflected sound will come as a repetition, not a prolonged effect like the reverberation. So, and then next off, we have a result of many thousand reflection in each second. So reverberation, you'll notice it enhancing effect, which is it comes and enhance the sound, not just once, but in a way that it feels very grand. But in a case for echo, it's just a one single distinct reflection, meaning you'll hear the original sound again. It becomes a repetition. So finally, you have comparison is that reflection reach the listener long enough to be heard as separate sound, and then for reverberation, reflection reach the listener too rapidly to be heard as separated sound. So when it comes to reverberation and echoes, they are actually basically just reflection of sound. But the difference between them is how fast they how fast we are able to perceive it, and then is it a repetition or is it an enhancement of the sound. But then sometimes due to how we build up the how we want the room acoustic to be, we do not want both of them. So when it comes to ending what is reverberation and echoes, they are basically just reflection of sound in a room. Okay, so next we have your definition of what is a reverberation of time. So it's actually the time taken for a sound to decay by 60 decibel from its original level. So it's in second. And then any decrease in sound level by 60 decibel is a drop. It's a lot of drop lah in the original sound power. Okay, so different activity will have different reverberation time. So for speech, we want to have not more than 1 second or in between zero point 0.5 to 1 second, and music 1 to 2 seconds. And then you can have short reverberation time as required for clarity of speech, and then longer can be used for enhancement of quality of music. So this is where room acoustic comes about. We Because we are in an enclosed space, then we want to reduce all these sound to, instead of it being an echo, we want to reduce it to become a reverberation. So to do that, we actually have a calculation and formula. So this formula is a Sabine formula. Usually, when it comes to scientists giving name, this is the guy who founded it lah. So it's a Sabine. This guy's name is Sabine something. Not sure what is it, but he's the one who come up with this formula. So he put his name there. This is usually the case for a lot of formula you find around lah. If you see formula with a name, then that is a person who invented it. So you are given this formula, which you don't have to memorize. I'll give it to you guys in a formula sheet, where T is the reverberation time that you want in a room, and then you have this constant 0.16 multiplied by your volume divided by your area. So to make use of this formula, you have this example 8. So how to calculate the reverberation of time? You'll be given a example here. So you have a volume of 5,000 meter cube, and then you are required currently this hall based on this 5,000 is giving you a reverberation time of 1.6. So you want to calculate what is the extra absorbance required. So the keyword is finding out what is the extra absorbance required to obtain a reverberation time of 1 second. So you're given a situation where you have a hall with 5,000 meter cube volume, and then currently this hall is giving you a reverberation time of 1.6 second. So you can write down all the information, the time given for this hall without any extra absorbent is 1.6 second. And then you want to reduce this reverberation time to 1 second. So you need to put in the extra absorbent. So you'll be required to use a formula which is T equals to 0.16 multiplied by V over A. So for the first T, with in this first in this hall with a reverberation time of 1.6 second, you first need to find out what is the area of extra adsorbent. So because this is A is equals to total adsorbent of room surface, by the nature of thing, the room will already have adsorbent inside it. So the first part is you want to find out what is the area of adsorbent for 1.6 using this formula. So once you solve it, you find that the first area with a 1.6 second of reverberation time actually have 500 meter square turbine. So the extra adsorbent area is called this meter square turbine. And then for the second area, for the second time, which is 1 second, you just do the same lah. You substitute it, and then you end up with 800 meter square turbine. So for this hall with 5,000 meter cube, when it has a reverberation time of 1.6 second, it actually have 500 meter square turbine. And then when you reduce the reverberation time to 1 second, then the adsorbent that's present in this hall is actually 800 meter square turbine. So when it comes to calculating the amount of extra adsorbent, then you just need to minus the 800 with the 500, and you get the answer, which is 300 meter square turbine. So this is a very simple example lah on how manipulating the reverberation time from 1 second to 1.6 second, you actually need additional 300 meter square turbine. Okay, so another example to showcase the usage of this formula, you have a lecture hall with 1,500 meter cube, and then you have different surface area. So instead of you finding out what is the area here, you are actually given all of this area, and then they are at a coefficient of 500 hertz. So you have to actually calculate what is the reverberation time of this hall when it's occupied by 100 people. So this question is a bit different lah. Instead of giving you the reverberation time, they are giving you the area. And then here is mentioned 500 hertz. So this one you can just ignore lah, because sound actually comes with a property which they have different frequency. But in this case, for the example, because they are at the same frequency, then you can just ignore them. So you want to make sure that they are at the same frequency, so you don't have to be bothered by them lah. This. Okay, next you have another new info, which is this hall is occupied by 100. So here you can just put in 100. Usually when it comes to this example, you'll be given a table, and then you'll be given area here, a value area, and also an adsorbent coefficient. So what you want to do with this table is you want to multiply the area with the adsorbent coefficient. Then this will come up with the total adsorbent for these surfaces and for the audience also. So you don't have to redraw the table. You can just multiply them together, and you get the value for your total adsorbent. So same case for the audience, you multiply them together, and you get a value of 99 meter square turbine when you add them all together. So the unit is already on top, but if you didn't do it in a table, so do make sure you put a meter square turbine here lah, if you are not doing it in a table form. So when you got the total adsorbent for all your other surface material and also for the audience, then you can put it into your formula, which is T equals to 0.16. This is constant lah. And then you have to multiply with your volume, which is already given, 1,500, and then divided by 99. So you solve it and you get 2.42. So this question just ends with you finding out the liberation time. So you just put 2.42 second. Do remember to end the question properly lah. And then for this question, they mentioned 500 hertz. So you just put it here. So example 9 is solved in this manner. So next we have another example. So the liberation time for this hall is 1.5. So you're given the liberation time, and then you have to calculate the area of acoustic tiling needed on the wall to achieve this liberation time. So you're given that this tiling, you do not know what is the area, but they are giving you the info that this tiling, the absorbance coefficient is 0.4, and then you have the composition of walls, ceiling, and floor. So in this case, you actually have an unknown here for the area for your tiles. So let's have a look at how to solve this question. So when it comes to having an unknown, then things will become a bit more complex. So you won't have a whole number. So that's why you need to do a bit of maths here, although it's not very complex. But if you follow through the method, then you actually be able to solve this question. So because you do not know what is the area for your tiles and your walls and your surface of the walls, you actually have to minus out the tiles. So why is this such case? So when it comes to reflection in a room, where does it reflect from? So it actually reflects from the wall. So, and also the question is mentioning the area is actually acoustic tiling on the wall. So that's why this tiles is actually a remaining area of the walls. So this is where the tiles and the walls come about lah, the unknown. So tiles will be S, the amount of tiles you want to put on the wall, and then you're given the wall area is 400 minus the remaining area not covered by the tiles. And then you have the remaining coefficient. So with this unknown, what you can do first is you just multiply them together. You'll get that S is 0.4 S, and then when it comes to wall, you multiply them together, you'll get 2 value, which is 8 minus 0.02 S. So for ceiling, floor, and audience, you get a whole number. You can add them all together and you get 99 plus 0.38 S. So this is still in a very good simplified form. So with this value, because you know the T is 1.5, which is given here, 1.5, and then the volume is 1.5. So based on the available information there, you can actually solve the question with this because you're given the time and also the volume. So you can substitute the area into the formula and then you end up with this equation. So from there on, you just need to move them around lah. Like here, you move it to here, and then you move this 1.5 to the other side of the equation, and then you'll be able to solve this equation. So based off that, you get that the area required for your tiles is 160.5 meters squared. So out of the 400 area, the S is actually 160.5 meters squared. Okay, so not that hard lah. So for your, just a quick reminder lah, for your exam, final exam, your calculation question, do practice on your example, although I give all the answer to you guys. You guys don't have to, because I want to make it easy for you guys don't have to print it out and write it in this. So let me just give it to you guys. But then when it comes to your final, you need to use a pen and a paper to write. So do a bit of practice because the level your final, the question, won't go very far from this example, from your lecture slides and also for your tutorial. So I put a lot of emphasis. Please do your tutorial because this is a good practice for you to prepare for your final. Okay, so finally, you have your additional material. So based on different material available, they have different absorbance coefficient. So at different frequency, the coefficient will be different. So we can have material, and then we can have the absorbent material inside the building. So usually this one is just additional material for you to use in your assignment. So based on what building you choose, then you can have a look at here, or you can search online to find out what is the sound reduction index or the absorbance coefficient and make use of this value for the calculation inside your assignment, which I will discuss next week. Okay, I think this is it for your topic 2. Any question?